Hello, my name is Mohammad Ruitavov, and in this video I want to talk about distributed transactions. So transactions are usually avoided by NoSQL databases to achieve higher scalability and availability. So the idea is that if we get rid of transactions altogether, we can scale much more easily and be more available. However, transactions are essential for many applications, and in reality, for many systems, it is much better to pay the cost of transactions than always coding around the lack of transactions. So distributed transactions are especially challenging for replicated data stores. So to provide distributed transactions for replicated data stores, we need to use some form of consensus for replica consistency, and of course some form of concurrency control for isolation. And different systems that provide distributed transactions for replicated data stores use consensus and concurrency control in different ways. So for example, a spanner that we will see in this video uses a partition level replication and use Paxos at the partition level for the consensus, and use two-phase locking for concurrency control. On the other hand, Calvin uses Paxos at a global level and use deterministic approach for concurrency control. And FoundationDB, another system, basically synchronously writes to all replica for replica consistency, and use optimistic concurrency control for concurrency control. So this is the outline of my talk in this video. I will first talk about serializability, and then we will see these three systems: Spanner, Calvin, and FoundationDB. So the nice thing about this selection is that these three systems tackle the same problem, which is providing strictly serializable distributed transactions with completely different approaches. So it is very nice to see them side by side and see what are the choices that we have if we want to provide distributed transactions for our partition and replicated database. Okay, so let's start with serializability. So serializability is the strongest isolation level that a transactional system can offer. It removes all possible anomalies due to concurrently running transactions. So when people talk about ACID transaction, they generally mean serializable transactions. However, some systems that claim to provide ACID transactions provide weaker isolation levels. So you need to always be careful when a system claims to be ACID to see what exactly what level of isolation that system is providing. So what is serializability? So serializability simply means that the database should appear to run transactions in some sequential order. So in other words, although we might run transaction concurrently, to the client it should appear that we are running transaction one after another. So serializability, as we said, is an isolation level, but it's not the only isolation level. We have weaker isolation levels, for example, read uncommitted, read committed, and a snapshot isolation. So for replicated data stores, in addition to the isolation, we have another dimension, which is the consistency between replicas, and this is very important. So at the highest level of consistency, we want linearizability, which is also known as strong consistency, that provides an illusion of having a single replica. So although we might have several replicas in our system and client can access each of these replicas, but these replicas are consistent to each other such that to the application and the client it appears that we have only a single replica. So we have weaker levels for consistency. We have, for example, sequential consistency, causal consistency, session guarantees, and of course eventual consistency. So it is very important to distinguish these two completely different dimensions, the isolation and consistency. So now let's see what is strict serializability. So if we go back to the definition of serializability, we said serializability simply means that the database should appear to run transaction in some sequential order. So that order could be any order. And under serializability, the database is allowed to change the order of transactions, for example, to achieve a better performance. And that's okay as long as transactions appear to the client that are executing in according to some sequential order. But in strict serializability, the database should respect the real-time order of the transaction. So more specifically, if transaction T1 commits before transaction T2 starts, then the system should appear to run T2 after T1. So under serializability, even when T2 starts after T1 commits, the database can switch the order of T1 and T2. But under strict serializability, the store is not allowed to do that, and it should respect the real-time order of the transactions. So in that sense, strict serializability for a replicated system is a combination of serializability and linearizability. Okay, so because it's a combination of these two, it provides two illusions. One illusion that transactions are running one after another due to the serializability, and the second illusion is that there is only one replica in the system because of linearizability. So why I say illusion? Because in reality, in practice, the database may run transactions concurrently, or we may have more than one replica. But a system that is strictly serializable provides this illusion that transactions are running one after another and there is only one replica in the system. So a strict serializability is the ultimate guarantee that you can ask for from a transactional system. It provides the highest level of replica consistency and highest level of isolation. So it's a very powerful property and is very nice thing to have for a transactional system. So now this is our problem. So how to provide strictly serializable distributed transactions for replicated and partition systems? So what are replicated and partition systems? Basically systems that our data is so big, so we cannot fit the data in a single machine, so we have to shard data. But on the other hand, to provide to have higher availability, durability, and be more scalable, we make copy of our data. So for each shard, we have a couple replica, right? So the data is sharded, shard 1, shard 2, shard 3, and shard 5. And each shard has a couple replicas. So now let's start with the first solution to this problem. So spanner. So suppose we have a single node database. Okay, very simple, just a simple node database. So a simple way to achieve serializability is by actually executing transactions in a serial order, right? So which is known as actual serial execution. So specifically, we have a single thread that this single thread receive transactions from a queue and execute them one by one. Very simple. So with this system, obviously we have a strict serializability. But we have a performance problem because each transaction must wait for its previous transactions, and even when transactions are completely unrelated to each other, touching different part of the data, because everything is serialized, all transaction must wait for all transaction before them. So now this is the question, how to allow concurrency while keeping serializability. Is there any way that for transactions that are unrelated, run them concurrently, but transactions that are conflicting, run them sequentially. Is there any way to do that? And the answer is yes. Using two-phase locking, we can do that. So I'm not going to cover two-phase locking. You can refer to any database textbook. You can also refer to my blog at MyDistributed.Systems and read about two-phase locking. But basically the idea is we have a lock for each key or a range of key, that whenever a transaction wants to access that key or range of key, it must obtain the lock for that key. And if the lock is obtained by a by another transaction, basically you have to wait. And so if you think about two-phase locking, again, it's great because it opens the door for concurrency without sacrificing serializability. So now this is the question. So this was for a single node database, but what about a distributed database? How to guarantee serializability for a sharded database? Can't we just send transaction to all shards that have part of the data that the transactions is touching and run two-phase locking on each of them? So unfortunately we cannot do that. The reason is, if we do this, then it is possible that we run same transaction with different order on different shards that may violate isolation. And the other issue is that it is possible that we commit a transaction in some shard but abort transaction on the other shard, because the two-phase locking algorithm sometimes needs to abort transaction to prevent deadlocks. And if two-phase locking aborts a transaction on shard 3 while the transaction has been committed on shard 1 and shard 2, then we have a transaction that has been committed halfway through, and this violates atomicity. So we cannot simply run two-phase locking on each shard. So how we can avoid this? The answer is using two-phase commit. So if we use an atomic commit protocol such as two-phase commit together with this two-phase locking, then all of those problems are solved. And so this combination guarantees that transactions are executed in the same order on all shards, and the transaction, all of the transaction will commit either on no shard or on all of the shards that are involved in the transaction. So I'm not going to cover the details of two-phase commit, but it's a very famous algorithm. You can refer to any textbook. But basically the idea is we have a coordinator and shards are participant, and the coordinator commit a transaction in two phases. In the first phase, it asks them to get prepared, and before acknowledging the first phase, each participant needs to make sure that it has received the transaction and is okay to commit the transaction, and it has durably locked the transaction. And in the second phase, the coordinator asks them to commit or abort based on the votes that it has received from the participant. So with the combination of two-phase commit and two-phase locking, we can guarantee atomicity and serializability. So that's cool, but we don't have any replication in this figure, right? What if we want to have replica? How we want to update data in the replica? So the answer is that we can have a replication group for each shard and run a consensus algorithm, for example Paxos, for each group, and then we can run two-phase commit on the leaders of this replication group. And this is exactly the idea that a spanner uses. So basically a spanner's main idea is running two PC and two PL over Paxos leader, and all the state of two PC and two PL are recorded in the consensus group. Okay, so if we only access leaders, then a strict serializability is guaranteed with this approach. However, when we create replicas, we want to scale our read by letting clients read data from any replica and not only the leaders. And so now this is the problem: how let read-only transaction be executed on any replica, and also how to prevent these read-only transactions from blocking other transactions. So Spanner supports read-only transactions through snapshot. So what is a snapshot? Basically, a snapshot reads data at a frozen point in time. So all previously committed transactions should be included in the snapshot, right? So the effect of all previously committed transactions should be reflected in the snapshot, and all uncommitted and all ongoing transaction should be excluded from the snapshot. So Spanner uses a multi-version concurrency control, or MVCC, for snapshots. And so basically each snapshot has a timestamp at which it wants to read the database. And for each key, we have a set of versions, each with different timestamp. And the database returns the version with the highest timestamp not greater than the snapshot time. So let's see an example. Suppose we want to read item X, and for this item we have 3 versions. We have a version with value 5 and timestamp 1. We have a version with value 3 and timestamp 4, and we have a version with value 10 and timestamp 6. And suppose the snapshot wants to read this item with time 5. So the snapshot time is 5 and it wants to read item X. So the Spanner returns the version with the highest timestamp not greater than the snapshot time, which is 5. So the version with the highest timestamp not greater than 5 is the second version with value 3. So this is the snapshot algorithm of Spanner. Again, each snapshot has a timestamp. Each snapshot wants to read a set of keys or item, so it go to the shards that are hosting that item, and each shard return a version with timestamp not greater than the snapshot time. Very simple. So to guarantee a strict serializability with this snapshot algorithm, we need to guarantee if transaction T1 commits before transaction T2 starts, then all versions written by T1 have a timestamp less than the timestamp assigned to versions written by T2. Let's see an example. So here we have 2 transactions, T1 and T2. So transaction T1 writes value V1 for item X, and transaction T2 writes value V2 for the same item. And transaction T2 starts after transaction T1 commits. So now we have 2 versions in the version chain for item X. We have one version with value V1 and timestamp T1, and the other version with value V2 and timestamp T2. So we say to guarantee a strict serializability, we have to guarantee that T2 is larger than T1. And any such versioning is called a proper versioning. But let's see why this proper versioning is necessary. Suppose we don't provide proper versioning. Suppose we violate that. And in this scenario, suppose we assign timestamp T1 and T2 such that T1 is greater than T2. Now a snapshot at time T3, which is greater than T1 and T2, wants to read item X. So since T1 is larger than T2 and T1 is smaller than T3, based on the snapshot algorithm that we just described, the system will return version with value V1. But by returning V1, the system violates strict serializability. Why? Because it appears that the system has ordered T2 before T1. And this violates the real-time order of the transaction, right? Remember that we said for strict serializability, we have to respect the real-time order. And when T2 starts after T1 commit, the real-time order requires that v2 should be the winning version, should be the final version. So by returning v1, we violate that. So that's why we need proper versioning to make sure our snapshot algorithm that we describe respect strict serializability. So now this is the question, how to achieve proper versioning. So if we had perfectly synchronized clocks, then the problem was solved. We would simply use system time as the timestamp, and we had proper versioning, very simple. But unfortunately, perfectly synchronized clocks are infeasible with today's technology, so all clock synchronization algorithms have always an error. So a spanner uses TrueTime that returns time as an interval instead of a point, right? So whenever you ask TrueTime what is the time, TrueTime return an interval, earliest and latest, and it is guaranteed that the real time is in this interval. So it is larger than earliest and smaller than the latest. So now suppose we have this TrueTime and we have this guarantee that the real time is between earliest and latest. Now the question is how we can achieve proper versioning with such an API. So the solution is this. At the commit time, a spanner reads the earliest and latest from TrueTime, and a spanner picks a timestamp t such that t is larger than the latest, right? So here transaction t starts. At some point it decides to commit transaction t. So at that point we ask TrueTime what is the time interval. So it returns an interval, and a spanner picks a timestamp that is greater than the latest value returned by the TrueTime. Then a spanner keeps asking earliest and latest from TrueTime and waits until earliest is larger than the timestamp that it has picked for the transaction before committing the transaction and returning success to the client. So it keep asking, and once the earliest goes higher than the timestamp, it commits the transaction at that point and returns success to the client. So with these two properties, a spanner guarantees that the timestamp that it assigns to each transaction is strictly greater than the real start time of the transaction and strictly smaller than the real commit time of the transaction. Okay. So now let's see how a spanner guarantees proper versioning. So basically we want to prove that whenever T2 starts after T1 commits, then timestamp of T2 is larger than timestamp of T1. Okay, so we have transaction T1, it starts and commits, and based on what we showed in the previous slide, we know that the timestamp that the spanner assigned to this transaction is between start and commit. So now transaction T2 starts, and based on the assumption, we know that transaction T2 starts after T1 commits. So again, based on what we showed in the previous slide, we know that the timestamp that the spanner assigns to T2 is larger than the start time of T2. And you can see based on this that it will be guaranteed that the timestamp of T2 will be larger than timestamp of T1. So this way you can see how using TrueTime spanner is providing a timestamping system that respect proper versioning. So to guarantee a strict serializability, we need followings invariant. First, we need proper versioning that we showed a spanner satisfies. So again, when T2 start after T1 commits, then timestamp of T2 should be larger than timestamp of T1. The second property that we have to satisfy is that the snapshot time should be larger than the timestamp of any previously committed transaction. So remember, we said a spanner supports read-only transaction through a snapshot. Each snapshot has a time, right? And we described what is the snapshot algorithm. But the question is, what should be the time that we assign to a snapshot? So a client requests a read-only transaction, we create a snapshot. So we have to specify a time. What should be the timestamp for the transaction? So the answer is a spanner picks, basically a spanner asks TrueTime return an interval, and a spanner picks the latest value returned by the TrueTime as the snapshot time. And this way, a spanner guarantees that the snapshot time is larger than the timestamp of any previously committed transaction. And let's see why. Suppose we have a transaction T, it starts and commit. Based on what we showed, we know that the timestamp of T is between start and commit. And then based on the assumption, we know that a snapshot start after T commit. And now it asks, at this point, it asks TrueTime and pick the latest as the snapshot time. And so again, so we have shown before that the timestamp of T is smaller than the real commit time of the transaction. And based on the assumption, we know snapshot start after T commits. And based on the TrueTime property, we know that latest is larger than the real time of the snapshot, right? And these all together prove that a snapshot time is larger than the timestamp of any previously committed transaction. So in addition to these invariants, we need another thing, that we have to make sure a replica is up to date enough when we want to read from the replica, right? And to make sure the replica is up to date enough and basically has all the versions up to a certain timestamp, we have a variable called tsafe that basically is the latest timestamp applied in a replica. And a snapshot blocks when snapshot time is larger than tsafe. So whenever a snapshot time is larger than tsafe, there is a possibility that we are missing some version in the version chain of a key. So we have to make sure that we have received all version and then run a snapshot algorithm, right? And this tsafe is exactly for that purpose. So if we have these three properties, 1, 2, and 3, then our snapshot algorithm guarantees strict serializability. Okay, so before going to summary, just to recap, I want to say that if we only needed read-write transaction, and we were okay to only go to the leaders, we didn't need any of this TrueTime and this snapshot algorithm, right? Just 2PC and 2PL was enough. The only reason that in a spanner we are using this TrueTime, proper versioning, snapshot, and everything is because we want to allow read-only transaction to go to any replica. And because of that, we have these details about the timestamp. Okay, so in summary, a spanner uses 2PC and 2PL over Paxos leaders to support serializability in a replicated and partition system. It uses MVCC to provide consistent snapshots, and it uses a TrueTime and wait out the uncertainty window to guarantee a strict serializability. So to read more, of course, you can go to the original paper by Google, and I also have a blog post on Spanner for more details and all the failure and details that you might be interested. You can go to this blog post. Okay, so now let's go to the second solution to this problem, the problem of providing a strictly serializable distributed transactions for replicated and partition systems. Okay, so we said by combination of 2PC and 2PL, we can achieve a strict serializability, and that is great. However, this combination has a problem, and the problem is whenever we obtain a lock in 2PL algorithm, in this solution we cannot release the lock even when a shard is done with a transaction before we receive the final answer or final decision from the coordinator, right? So in a single node database, the transaction manager get the locks and execute the transaction and quickly release all the locks at the end of the transaction. But when we are running two-phase locking and two-phase commit, the shard cannot do that, and it must wait for the coordinator of the 2PC. And 2PC is a time-consuming procedure, right? Because it's over network, and in a worst case, the coordinator or some of the shard may be slow or even crashed, and then during the whole time we cannot really release the lock. So this increases the contention footprint of the transactions, which in turn result in a lower throughput. And this is the problem of this idea of combining 2PC and 2PL. So remember, we needed 2PC to deal with non-determinism of 2PL, right? Remember, we said if we just run 2PL without 2PC, it is possible that 2PL run transactions with different order on different shards, or even it may may abort some transaction in some shard, but commit the transaction in the other shard. So we had some non-determinism in the 2PL algorithm, and we needed to combine 2PL with 2PC to prevent that non-determinism. So Calvin's idea is, if somehow we get rid of this non-determinism, then we don't need 2PC anymore, right? If we make sure that the order is guaranteed on all shards, and if we make sure that a transaction will commit on all shards, then we don't have any non-determinism, and we don't need 2PC anymore. And it is very interesting idea. But the question is how to achieve serializability, concurrency, and determinism, right? So 2PL, we said, is great because it opens the door for concurrency while keeping serializability, but is non-deterministic. How we can keep concurrency and serializability and add determinism? And the answer is deterministic locking. We will see the details of deterministic locking, but basically in deterministic locking, a single thread globally orders all transactions, and all shards will follow this order. So you may ask, then what is the difference between deterministic locking or this deterministic approach and actual serial execution? What is the difference? Because in both of them, we say we have a single thread. The difference is, in the actual serial execution, a single thread orders and execute transactions. So we have serializability, but we don't have concurrency. But with deterministic locking, a single thread orders transaction, but we can execute transaction concurrently. When doing so does not violate the order. So we have serializability, we also have concurrency. So you may ask, what about the atomicity? Because 2PC, after all, is an atomic commit protocol. And it seems its main purpose is to provide atomicity, to make sure that transaction will commit on all shards. How we can provide atomicity if we don't use 2PC? So the Calvin answer is that we make sure each transaction is durably locked before sending the transaction to any shard. So basically the idea is that upfront in the system we have a log that is a global log, is a replicated global log that log all the transactions durably. And this log make all the transaction durable and also defines the order of the transaction. And then all the shards will get the transaction from this log, and all of them are guaranteed to execute transaction in the exact same order by using deterministic locking, as we will talk in the upcoming slides. So you can see that this idea requires something, that the transaction must be in the form of a stored procedure. So we cannot have interactive transactions that the client first reads something and then based on that write something else, and basically it has in a conversation with the servers. We cannot do that in Calvin. We can submit a logic, and in that logic we can say read something and based on that write something else, but the whole logic should be appended to this replicated log in a single shot. And we didn't have this limitation in Spanner, right? In the Spanner, the client we can basically execute the transaction logic on the client side, but in Calvin we cannot do that, and the client should submit its logic in a single shot. Okay, so now let's go to deterministic locking and see what is this deterministic locking that has this nice property of combining together serializability, concurrency, and determinism. So we have a log. This log defines the order of the transactions. So for each transaction, we have to know the full read and write sets. And this is another limitation of Calvin, because in Calvin, each transaction must know its full read and write sets. And we will talk about some form of transactions that they don't know their full read and write set until they execute their logic. We will talk about that. But in general, so transaction to schedule each transaction in Calvin, we have to know the full read and write set. So we have a scheduler thread. This is a single thread that reads from this log, and we have a log table that for each key or a range of key we have log, and this scheduler receive and read this transaction one by one, and for each transaction it requests the lock for the keys in the read and write sets of the transaction. So here, for example, for transaction T1, it requests the K1, K2, and K5. For T2, K1 and K5. For T3, K2 and K5. And for T4, K3 and K6. So any transaction that successfully obtained all of the locks for all of the keys in its read and write set is ready to go and can be executed. So here, for example, T1 is ready, right, because it has received K1, K2, and K5. T2 is not ready, T3 is not ready, and T4 is also ready because it has obtained K3 and K6. So these two transactions are ready to go. So here where the concurrency of deterministic locking shows up, these two transactions can be executed concurrently, right? So in the actual serial execution we cannot do that, but with deterministic locking we can do that. So the other two transactions, T2 and T3, must wait for T1. Okay, so we said in Calvin each transaction must be in the form of the stored procedure, right? But the question is how we can execute a stored procedure in a distributed environment, right? Suppose we have a stored procedure, very simple. It set the value of X to Y, right? So we append this transaction to our durable log. Now suppose X and Y are hosted by two different shards. So suppose Y is hosted by shard 3 while X is hosted by shard 1. So because two shards, shard 1 and shard 3, are involved in this transaction, we send the transaction to both of them. However, shard 1 cannot execute the logic of the transaction because it doesn't know what is the value of y. So in this situation, shard 3 sends the value of y to shard 1, and now shard 1 can execute the transaction. So in Calvin, to execute transaction, shards need to talk to each other, right? To basically have all the value necessary to complete the logic of the transaction. Okay, so in Calvin, everything should be deterministic. So we said how the order is deterministically defined by the replicated log, but the logic of the transaction itself must be deterministic. Suppose we have this transaction. We have a transaction that generates a random value, and if the random value is greater than 0.5, it sets the value of x and y to 1. Otherwise, it sets the value of x and y to 0, right? So we have a randomness. We have a non-determinism in this code. So now suppose we add the transaction to our durable log. Again, y and x are hosted by two different shards. So when we send this transaction in to these shards, each of them will execute the logic of the transaction independently, right? So it is quite likely that these two shards may end up in a different random value, right? One of them can generate 0.1, the other may generate 0.8. And one of them set the value of y or x to 1, the other set value to 0. Okay, so here we may have y set to 1 and x set to 0. And this is not desired, because the transaction wants to set both x and y to 1 or both of them to 0. But because of the non-determinism in the code of the stored procedure, we have this problem. So the Calvin solution to this problem is that we should have a pre-processing layer that basically check the code of the transaction and removes all sources of non-determinism. So here, when the preprocessor sees that we are generating a random number, it replaces the random number with an absolute value, suppose 0.8. So basically it transforms transaction T to one that doesn't generate a random value. And that the T prime transaction, which is a transform transaction, simply sets the value of x and y to 1. Now both shards will set the value of x and y to 1. Okay, let's go back to a problem that we briefly mentioned when we were talking about deterministic locking. So we said deterministic locking requires to know the full read and write set for each transaction. However, some transactions need to execute their logic first to finalize their read and write set. And these transactions are called dependent transactions. For example, here we have a transaction T that reads value of x, and if x is equal to 1, it writes value 2 for y, otherwise it writes 2 to z. So the final read and write set, basically the final write set of this transaction depends on the value of y. But we don't know this value until we execute the transaction, and that is a problem. So Calvin's solution to deal with dependent transaction is to execute and basically schedule dependent transactions in two phases. In the first phase, we read all necessary data required to finalize the read and write sets. And in the second phase, we schedule the transaction to be executed just like other transactions. However, we have a problem. The problem is that the values that we read in phase 1 might change between phase 1 and phase 2. So in this situation, we have a problem. So the Calvin solution for this problem is that before executing phase 2, we must validate the values read in phase 1. If those values has not changed, we are good to go. But if those values have changed, we must start over. And you can imagine that if value change frequently, then to execute the dependent transaction in Calvin, we may need to try several times. Or the transaction may even start forever. And this is another problem in Calvin. Okay, so now let's talk about yet another problem in Calvin. Consider two transactions, T1 and T2. So transaction T1 reads value x1, x2, and x100 and write 2 for y. And transaction T2 reads value y. Okay, so in a two-phase locking, in a system with two-phase locking, what will happen if we want to execute these two transactions? Well, the transaction manager is supposed to start with T1. So it requests the lock for x1 and read x1. Then it requests lock for x2 and reads x2. And this goes until x100. And then it writes 2 for y. So in 2PL, the transaction manager requests this lock gradually, not all at the beginning. It requests this lock gradually, and once it gets the lock, it holds the lock until the end of the transaction. So it is possible in 2PL that T2 go ahead and get the lock for y while T1 is still in line 1, and T2 get executed and done. But in deterministic locking, we cannot do that. In deterministic locking, all locks must be acquired at the beginning before executing the transaction. So T1 will get all the locks x1, x2, and x100 and y. And suppose T2 comes, but T2 cannot be executed until T1 finish, because T2 cannot get the lock for y. And this is a problem when we are running our transaction on a slow drive. So the Calvin solution to this problem is that we should delay appending T1 to global lock. So whenever we see that we have a transaction that needs to read many keys, we have to delay appending this transaction to log. And meanwhile, we should ask shards that host keys that this transaction wants to read, ask them to load those data from disk to the memory and basically warm them up. And then by the time that T will go to those shards, the data is ready in the memory, so it won't get too long, and it won't block other transaction for too long. But the issue is that it is very hard to estimate accurate amount of time for delaying the transaction, right? So in practice, we either underestimate that by underestimating this required time when we want to actually execute T1, the data is not ready in the memory, and then we block, and which result in lower throughput, or we overestimate that time, that this way we block T1 itself, and this result in the higher latency. Okay, so in summary, we see that Calvin uses a replicated lock up front, at the front of the system, and this lock orders transaction requests and plays the role of a write-ahead lock for the system, providing atomicity and durability. So Calvin removes the need for 2PC by removing the non-determinism caused by 2PL, by replacing 2PL with a deterministic locking on each participant. So Calvin only supports transactions in the form of stored procedures, and some of the challenges in Calvin are problem in executing dependent transactions, and the problem of slow storage. To read more about Calvin, you can read the original paper. I also have a blog post on Calvin. Calvin is usually compared with the spanner because are completely two different approaches. There are blog posts on this comparison. If you like, you can read them. Some of them are in favor of Calvin, some of them are in favor of spanner. This is good, so you can read them and see which one is better for your system. Okay, so now let's go to the final solution, or I mean the third solution for this problem, which is FoundationDB. Okay. So both Spanner and Calvin use a pessimistic concurrency control. So they prevent any possibility of violation of serializability by locking the keys, right? So they lock the key, and by locking the key, they eliminate any possibility for violation of serializability. So FoundationDB uses an alternative approach, which is known as optimistic concurrency control, or OCC. So in OCC, we don't lock anything and let transactions access keys freely. And at the commit time, we make sure that committing the transaction does not violate serializability, right? So it's a very optimistic. So we say hopefully it doesn't cause any issue, but at the commit time I check, and if I see that committing a particular transaction violates serializability, then I abort the transaction. So the question is how to make sure committing a transaction does not violate the serializability, right? This is the key part. So the answer is that if none of the values read by the transaction is overwritten by another committed transaction, then we can be sure that committing a transaction doesn't violate serializability. Thus, to use this approach, we need to keep track of all versions read by a transaction, and at the commit time, we need to check if they are overwritten by previously committed transactions or not. And this process is called conflict checking. So if you want to do the conflict checking by reading from the database, it could be very slow, because if you want to, for each transaction, if you want to check if any of this value has changed or not, if we go to the database and to check that, it could be very slow and it's not efficient. So FoundationDB's solution to this is to use a cache that basically has the most recent committed version, and use this cache for conflict checking. So currently FoundationDB keeps a cache of versions written in the past 5 seconds in the system, and this is enough to do the conflict checking. Okay, so this is the concurrency control in FoundationDB. So the client first requests the read version from a transaction subsystem, and this read version is very similar to a snapshot time in the spanner, right? So then with this read version, the client directly go to the storage node and makes its read operation, and it also includes its read version with each read operation. And similar to a spanner, we have a version chain for each key, and then FoundationDB returns the most recent version, not newer than the read version. And again, FoundationDB keeps a version that are written in the past 5 seconds, so we don't keep versions forever, right? And then this is for read. For writes are very simple in FoundationDB. They will be buffered at the client. So for write, the client doesn't do anything with the database. It's just buffer all of the write on its side. And once the client is ready to commit its transaction, it sends a commit request to the transaction subsystem, and the client includes its read and write set. And the transaction subsystem does the conflict checking. If any of the values read by the transaction is overwritten, the conflict checking aborts the transaction. Otherwise, it commits the transaction. And when it commits, it returns to the client, and the shards, the storage node basically will get the update from the transaction subsystem and apply them on the storage nodes. Okay, so that was the concurrency control. And what about the consensus? Right? Remember, we said any distributed transaction, any system that provides distributed transaction internally have to solve these two problems and use some form of consensus and concurrency control. So we said a spanner uses Paxos at the replica level, Calvin uses Paxos at the global level. So FoundationDB also use consensus, use Paxos to pick master that assign timestamp. But the main part, which is the write path, in the main part, it doesn't use Paxos or Raft or this kind of consensus algorithm. It's just simply synchronously write to all replicas before returning to the client. And you may ask, what about the replica failure? If one of these replica that we want to write to all of them fail, what will happen? So the FoundationDB, as we will cover this part, creates a new replica to always have the desired number of healthy replicas. So some nodes must be reserved to deal with these failure cases. Okay, so now let's go to the details of transaction subsystem. Okay, so in the transaction subsystem, we have a set of coordinators. These coordinators run a consensus protocol, for example, Paxos, and they pick a cluster controller. So any component in the transaction subsystem will register itself to this cluster controller. So the cluster controller also picks a master, and we have a set of proxies. These proxies talk to the client. We have a set of transaction logs, and suppose here we have a transaction log that is replicated. So we have 3 replica of this transaction log, and we have a set of resolvers that do the job of conflict checking. So whenever the client requests a read version from the transaction subsystem, this request goes to one of the proxies, and so to guarantee a strict serializability, just like a spanner that's needed to assign timestamp to the snapshot, here we need to assign a read version to the client that is larger than the timestamp of any previously committed transaction, right? So that's why this proxy asks all other proxies that what is your highest committed version, and then this proxy picks the maximum value of all of the timestamp of committed transaction as a read version and returns it to the client. So the client makes its read operation and buffer its writes, and then once it's ready, it submits a request to the transaction subsystem that includes its reads and writes set. And again, this request will go to one of the proxies. Now the proxy has the read and write set. So first it gets a commit version from the master, and then it talks to the resolvers and asks them to do the conflict checking. And each resolver return its vote, whether commit or abort the transaction. And whenever a resolver doesn't see any problem with a transaction, it updates its cache with the commit version received by the proxy. If all of the resolvers said yes to a transaction, the proxy decides to commit the transaction. So it appends this transaction to all of the replicas of the transaction log before returning to the client. After it appends all of these, appends the transaction to all of these transaction log, it returns success to the client. And then the storage nodes will get these updates from these transaction logs. So each storage node each storage node reads update from one of these replica. Okay, so that was the happy path. What about the failure? So FoundationDB uses a single recovery process for failures of any component in the transaction subsystem, right? So we have different components. We have coordinator, cluster controller, master, transaction logs, proxies, and resolvers, right? So the master always monitors the health of all of these components, and whenever any of them fail, master terminates itself. And once the cluster controller sees that the master has terminated, and the cluster controller picks a new master, and this recovery process starts. And whenever the cluster controller itself crash, the consensus group picks a new cluster controller, then the cluster controller picks a new master. Again, the recovery process will kick in. Yeah. Okay. So, but what is this recovery process? So, in the recovery process, the new master replaces all components in the transaction subsystem with new instances. So it will start new proxies, new resolvers, new transaction logs, right? And then the system does not accept new requests during recovery. So before resuming the traffic, the new master figures out the recovery version. So what is the recovery version? Basically is a timestamp at which the master considers taking ownership of the database. So it must be greater than the timestamp of any transaction committed by previous master. And all transactions timestamp assigned by the new master will be greater than the recovery version, right? So to find out the right recovery version, the new master asks all healthy transaction logs following values. The first value is the durable version, or DV, which is the highest timestamp appended to the transaction log. And the other is non-committed version, or KCV, which is the highest version that a transaction log knows that a proxy has appended to all transaction logs. Let's see an example. Here we have 3 transaction logs. Transactions 1 and 2 have been appended to all of these 3 logs, but transaction 3 has been appended only to the first log. And the proxy informs transaction log about the highest timestamp that it has appended to all of the transaction log. So here, suppose proxy informs the first transaction log that I have appended all transaction up to 2 to all transaction log, but this proxy has not yet informed the other 2 transaction logs. Now, at this moment, if you ask the first transaction log what are DV and KCV, it will return 3 for DV and return 2 for KCV. Why? Because the highest timestamp appended to the transaction log is 3, and the highest version that the transaction log knows that the proxy has appended to all transaction logs is 2. But if you ask the other 2 transaction log, they will return 2 and 1 for DV and KCV. Okay, so after receiving all of these DVs and KCVs, the new master picks the minimum of DVs as the recovery version. So let's see why it picks the minimum. The reason is, remember that we said in FoundationDB, each transaction must be synchronously appended to all replica of the transaction log before returning to the client, right? So then each transaction must be appended to all transaction logs, all replica of the transaction log must know about any committed transaction. So by taking the minimum, we are sure that we are basically there is no committed transaction with a timestamp greater than the minimum of DVs, right? Because if that transaction was committed, then the timestamp would be appear in all transaction logs. Okay, so let's see an example. Suppose again we have 3 replica of the transaction log. The new master comes and suppose the first transaction log has crashed. So the new master comes, it asks the other 2 transaction logs, the DV and KCV. So the second transaction log return 110 and 90 for DV and KCV, and the third transaction log return 120 and 95. So the master picks 110 as the recovery version because it's the minimum. Okay, so now look at the KCVs. The master has received 90 and 95. So when KCV is 95, based on the definition of the KCV, we know that all transactions with version less than or equal to 95 are persisted to 3 replicas, right? Because we know that all of them has been appended to all transaction logs. So whenever the recovery version is 110, we know that all future transactions with versions greater than 110 will be persisted to 3 replicas, because we know we won't commit any transaction unless we are sure that that transaction has been appended to all transaction logs. So all future transaction will have 3 replica. Okay, so before and equal to 95 we have 3 replica. Larger than 110 also we have 3 replica. But in the range between 95 and 110, we don't know if we have enough replica for each for those transactions that are in this interval. So to make sure that we have enough replica for each transaction that has been committed, the new master, before opening up for the business and accepting new transaction, it first copies all the transaction in the range of maximum KCVs plus 1 to the recovery version to the new transaction log. So here the new master copies the all transaction in the range of 96 to 110 to the new transaction logs before accepting new transactions. Okay, and so this is the after this, the new master and the new generation of the database is ready to accept a request, and this is the unified recovery process in FoundationDB. So in summary, we saw that FoundationDB uses MVCC to provide isolated snapshots to read, and by making sure that the snapshot time is always greater than the timestamp of any previously committed version, it guarantees linearizability, just like a spanner. So to replicate transaction logs, FoundationDB does not use Paxos or Raft. Instead, it requires a quorum size equal to the replication factor. And in case of a replica failure, it creates a new replica to have the required quorum size. So all failures of the transaction subsystem are handled uniformly by a single recovery process. So to read more, there are a couple videos from FoundationDB Summit, and there are a couple blog posts you can refer. I also have a detailed blog post about FoundationDB. If you are interested, you can refer to these posts too. Okay, so now let's go to the conclusion. We said strict serializability is the highest level of consistency and isolation. So to provide a strict serializability for replicated data store, we need to use some form of consensus and some form of concurrency control. We reviewed 3 different systems providing strict serializability. A spanner uses 2PC and 2PL over Paxos leaders. Calvin uses determinism, and FoundationDB uses optimistic concurrency control. So to read more, again, you can go to my weblog. So in this video, I focused on distributed transactions for a single database, for a single distributed database. Another interesting problem is providing distributed transactions for microservices. And providing distributed transactions for microservices is very challenging because we have lots more component, and traditional approach of using 2PC doesn't work very well for microservices. So at eBay, we have designed a protocol named Greet that provides strictly serializable distributed transactions across microservices. And if you are interested, you can refer to eBay Tech blog to learn more about Greet. So thank you very much for your attention. If you have any question or comments, please let me know. Thank you.